Somewhere above the Columbia Basin, in the dead middle of the night, something the size of a beach ball tore through the sky at more than 30,000 miles an hour and blew apart with the force of 10 tons of TNT. And not one observatory, satellite, or survey program on the planet saw it coming. Nobody had a warning to give. That's not a scandal. It's just where we currently stand with objects this small, and the story of how we piece together what actually happened that night says as much about the limits of our detection systems as it does about the rock itself. It happened at 12:48 in the morning Pacific time on Friday the 14th of August. A chunk of asteroid, something like 16 inches across, hit the atmosphere over central Washington and came apart 4 seconds later. People in 4 different places watched it happen: Washington State, Oregon, Idaho, and across the border in British Columbia. The flash was strong enough that people down in the Spokane area were woken up by it, grabbed their phones, and found their doorbell cameras had already caught the whole thing without them lifting a finger. One man in Spokane Valley said his first thought was that something had gone wrong at a neighbor's place. It took him a second to realize the light had come from directly overhead, not from next door. On its own, that's a nice local story and nothing more. A bright light, a loud rumble, a bit of excitement over breakfast. What makes it worth digging into is what happened after. A set of instruments that were never built to track meteors ended up recording this one in remarkable detail. And when you actually run the numbers those instruments produced, one of them doesn't add up. There's also a direction problem buried in the data, a heading that lines up a little too neatly with a pattern nobody in the meteor community has been able to explain since earlier this year. And underneath all of it is a flat admission from the people whose entire job is watching the sky for this kind of thing. They had no idea it was coming, and with the tools available right now, there was no way they could have known. Robert Lunsford, who monitors fireball reports for the American Meteor Society, put it about as plainly as it can be put. Fireballs, he said, are always going to surprise us. An object has to be enormous before anyone can spot it on its way in, and this one wasn't enormous by any stretch. NASA eventually pegged it at roughly 16 inches across. That's smaller than a beach ball, and it's the reason nothing flagged it in advance. What NASA published afterward, though, was oddly precise for something so small, and it's worth walking through because everything downstream depends on it. According to their reconstruction, the object started glowing at an altitude of about 78 kilometers directly above the town of Soap Lake, Washington. It was moving at 14.6 kilometers a second. NASA converted that for public consumption as roughly 32,800 miles an hour. From there, it kept heading north, covering something like 36 miles, through the upper atmosphere before it broke apart at around 45.5 kilometers up, which works out to about 28 miles above a spot in Douglas County called Sims Corner. All told, the object weighed somewhere around 170 pounds. A rock about the size of a beach ball, moving faster than a rifle bullet, silently crossing the sky in the dark. So, how do you even track something like that? NASA leaned on 3 separate sources, and only one of them was actually designed for this job. First came the eyewitnesses. Nearly 250 reports had been logged with the American Meteor Society by the end of that Friday, coming in from Washington, the Columbia River corridor, northern Oregon, Idaho, and British Columbia. By later that day, the count had climbed past 260. Second were 3 ordinary public webcams that happened to be pointed at the right patch of sky at the right moment and happened to be accessible afterward. Not a dedicated meteor camera network, just 3 cameras that got lucky. The third source is the one worth pausing on. The lightning mappers riding on NOAA's GOES weather satellites picked the event up too. Those instruments exist to watch for lightning strikes. They're tuned to a very specific wavelength of light, the atomic oxygen line at 777.4 nanometers. And it turns out a rock exploding in the upper atmosphere throws off exactly that kind of flash. Anyone who followed the daylight fireball that broke apart over New England back in May will recognize the pattern. That one was caught the same way by a satellite instrument that has nothing to do with meteors. Right now, a weather satellite's lightning sensor is one of the more dependable tools North America has for catching these events, despite nobody ever designing it for that purpose. That's not a coincidence limited to this one case. It's a pattern that keeps showing up. But the strangest bit of evidence in this whole event has nothing to do with cameras or satellites at all. When the object broke apart 28 miles above the ground, it sent a pressure wave rippling outward, and that wave was picked up by infrasound sensors that the U.S. Geological Survey has installed at 5 volcanoes in the Cascades: Glacier Peak, Mount Rainier, Mount Adams, Mount St. Helens, and Mount Hood. The signal reached those 5 stations between 12:55 and 1:10 that morning, anywhere from about 7 to 22 minutes after the explosion at 12:48. That spread isn't some mystery gap. It's simply physics. Infrasound moves through the air at around 0.34 kilometers a second, so the differences in arrival time map directly onto how far each station sat from the blast, somewhere between 140 and 440 kilometers away. The math checks out cleanly, but But look at what these instruments actually are. They're volcano monitors bolted onto the sides of cascade peaks, specifically to listen for eruptions, rockfalls, mud flows, and gas venting. They exist because Mount St. Helens killed 57 people in 1980, and the agencies responsible decided they never wanted to be caught off guard by a volcano again. On this particular Friday morning, instead of a volcano, they heard a rock falling out of space. The Cascades Volcano Observatory put out its usual weekly bulletin at 11:06 that same morning, confirming that every volcano across Oregon and Washington remained at normal background activity. In the span of a few hours, that observatory had looked at an odd pressure signal showing up on 5 of its own sensors, worked out that it wasn't volcanic, and said so in public. That's a fairly remarkable bit of quiet, competent detective work. And it matters for more than just this one event, because the United States doesn't actually have a dedicated national network for catching bolide infrasound. What exists is a patchwork, the international system built to catch nuclear weapons tests, a scattering of research arrays, and volcano monitoring. Stations like these 5. This event got recorded as well as it did purely because it happened to detonate inside the listening range of a volcano observatory. Something identical exploding over the Great Plains would have registered on far fewer instruments. In short, we caught this one because we got lucky. And that point is worth remembering because it comes back around later. The speed of the object is doing more heavy lifting in this story than any other single figure. 14.6 kilometers a second sounds like an enormous number, and by human standards it obviously is. But measured against the range of things that fall into Earth's atmosphere, it's actually on the slow end. The Perseid meteor shower, which was still active that same night, having peaked a day or two earlier, throws particles into the atmosphere at around 59 kilometers a second. This object was moving at roughly a quarter of that speed. NASA was explicit that this wasn't a Perseid fragment at all. Their language left no ambiguity. It was described instead as a sporadic meteor, jargon for a rock with no connection to any known shower or comet, no scheduled appearance on anyone's calendar, just a body that had been quietly orbiting the sun on its own path until Earth happened to run into it. A speed that low tells you something specific about where the object came from. It means its orbit around the sun was close to Earth's own. Low eccentricity, low inclination, roughly 1 astronomical unit from the sun, moving in the same direction we do, and in roughly the same plane. Earth essentially caught up to it from behind, rather than meeting it head-on. That's a very different kind of object from a fast-moving shower particle, arriving on a backward, steeply inclined path. There's a small inconsistency worth flagging in the public record. Lunsford, speaking to a local paper before NASA's official numbers were out, estimated the speed at around 25 kilometers a second, nearly triple what NASA later calculated. That kind of gap is no unusual. Eyewitness-based speed estimates tend to run high, almost as a rule, and a formal trajectory solution pieced together from satellite readings, camera footage, and cross-referenced witness reports is simply more reliable than a same-day field guess. Here's where things get genuinely strange, and it's worth being upfront that the honest explanation is far less dramatic than the one that started making the rounds online, though it's still worth sitting with for a moment. Take NASA's own numbers and just do the arithmetic. 170 pounds converts to about 77.1 kilograms. An object of that mass, moving at 14,600 meters a second, carries a kinetic energy of 1/2 times mass times velocity squared. Work that out, and you get roughly 8.22 billion joules. 1 ton of TNT equivalent energy is about 4.184 billion joules. So the total kinetic energy in a 170-pound rock moving at that speed, assuming every last bit of it converted with zero loss, comes out to about 1.96 tons of TNT. But NASA's own published figure for the energy, released when the object broke apart, is 10 tons of TNT. Those two numbers are off by roughly a... Run the same calculation for the Perseid radiant instead, and you get an altitude of 39.7 degrees at an azimuth of 43.5 degrees northeast. A meteor radiating from that point would travel toward the southwest, the exact opposite of what actually happened. So 4 separate threads line up in the same direction. The travel direction matches the anti-Helian source. The speed of 14.6 kilometers a second sits squarely in the range, typical of that source, and nowhere near shower speeds. The entry angle fits, and the object's overall behavior fits too, but it held together down to 45 kilometers, released enough energy to produce audible sonic booms at ground level, and may well have dropped fragments. That's asteroidal behavior, and anti-Helian source bodies are asteroidal by nature. On its own, that would be a mildly interesting technical footnote and nothing more, except for something that happened earlier this year. Back in March, the American Meteor Society put out an analysis covering the first 3 months of 2026. They gathered every fireball from that quarter with a resolvable trajectory. 67 of them worked out. In the sky each one had come from, and compared the results against the average from 2021 through 2025. The tight anti-Helian zone alone had produced 14 events against an expected baseline of 3.6, a statistical excess of about 4.1 sigma, which, under standard probability modeling, works out to something like a 1 in 40,000 result, and the highest sky density ever recorded in that zone, double the previous record. 22 of the 67 trajectory-resolved fireballs that quarter fit the textbook anti-Helian pattern. Low inclination prograde orbits, shallow entry angles, arriving at 3 to 4 times the normal rate. A second, separate cluster turned out even stranger. 12 events that quarter radiated from points above 70 degrees of declination, deep in the far northern sky, against an expected baseline of just 2.4, a 4.3 sigma excess, or roughly 1 in 118,000, in a category where the previous single-year high had only ever reached 5. To be fair to the skeptical read, and it deserves airing, the radiant calculation for this particular August event is a derived figure, not something NASA formally published. It comes from NASA's own start and end coordinates, run through the geometry, but solutions built this way typically carry radiant uncertainties of 10 to 20 degrees. And because the anti-Helian source is broad and essentially always active, a meaningful share of ordinary sporadic fireballs on any given night will naturally trace back to it, which is exactly why the excess identified back in March had to be teased out statistically rather than simply noticed by eye. One event by itself proves nothing. What it is, at most, is a single data point landing in an interesting spot on a map that was already drawing attention. There's a wrinkle here, and it's the reason this particular story isn't fully settled. In July, a researcher at NASA's Meteorite Environment Office named Althea Moorhead published a paper with a memorably dry title, something to the effect of a cornucopia of null results. She ran statistical regression on the American Meteor Society's fireball counts and found that the total number of reported events in early 2026 fit comfortably within the normal range of activity, with little support for what people had started calling the February fireball surge. That finding holds up on its own terms, but it's worth being precise about what it actually tested. It tested raw counts, how many fireballs got reported overall. It did not test where those fireballs came from. Those are two different questions, and a regression model built around total reported events can't say anything about why 22 of 67 trajectory-resolved fireballs that quarter clustered in one narrow strip of the sky. There's an added irony buried in this, too. The American Meteor Society itself had already acknowledged that its raw count data was statistically overdispersed, and that once you apply a negative binomial model instead of a simple Poisson one, the apparent excess in total counts drops to about 1.8 sigma, not statistically significant. So the null result that made headlines in July actually confirmed, something nobody serious was claiming in the first place, while leaving the directional excess completely untouched. Alongside that directional pattern sat two other physical facts from that same quarter that are harder to wave away. Sonic booms were reported on 82.5% of the larger events, and 3 separate meteorites were recovered within about 10 days of each other, against a worldwide baseline of roughly 10 recoveries a year. Put it all together, and the honest position looks something like this. The strongest piece of evidence still standing from the whole 2026 fireball anomaly is a direction, not a count. And in mid-August, something arrived from approximately that direction, at approximately that speed, at approximately that entry angle over Washington State. It doesn't prove anything on its own. It's simply one more entry in a column of unexplained data points. And before anyone runs too far with that, it's worth being blunt about the physics. The idea that something is being deliberately aimed at us gets the actual science backward. The anti-Helian source is about as ordinary a neighborhood of the inner solar system as exists, precisely where you'd expect a stream of prograde, low-inclination rubble to originate under completely natural circumstances. The word carrying all the weight here is unexplained, and unexplained is not the same thing as directed. The most plausible explanation on the table is that Earth's orbit is currently passing through a stream of debris left behind by a relatively recent asteroid breakup. That would still be genuinely new science. It would also be entirely natural. There's still one piece of this puzzle that could get resolved, and it may be sitting on the ground in eastern Washington right now. NASA's release noted that Doppler weather radar picked up signs that small fragments of the object might have reached the surface. That technique sounds unlikely, but actually works fairly well. It's the same method used back in March after the Houston fireball. Falling meteorites show up on weather radar as small, non-meteorological echoes drifting downward in the minutes right after an airburst. And those returns can narrow a search area, called a strewn field, down to just a few kilometers. Lunsford, speaking before NASA's formal trajectory was released, guessed that fragments might have landed somewhere near Bridgeport or Brewster. NASA's own endpoint for the fragmentation event puts it above Sims Corner instead. All of those spots sit within Douglas County, in the channeled scablands north of the Columbia River, open shrub steppe and dryland wheat country, which happens to be about as good as terrain gets for spotting a fist-sized black rock lying on open ground. As of now, no recovery has been publicly announced. That's worth stating plainly, because these searches frequently turn up nothing at all, and the absence of an announcement isn't evidence that anything is being withheld. For a sense of scale, this was actually a fairly modest event by recent standards. Back in March, a fireball over Ohio involved an object of roughly 7 tons and about 2 meters across, releasing something like 250 tons of TNT equivalent energy. 4 days after that, a fireball over Houston involved an object of around 1 ton, broke apart 29 miles up, released about 26 tons of energy, and dropped a fragment straight through someone's roof. The Washington event on August 14th, by comparison, involved a 170-pound object releasing roughly 10 tons of energy, the smallest of the three by a wide margin, and it still lit up the sky across 4 jurisdictions and rang out on 5 separate volcano monitoring stations. If fragments do turn up near Sims Corner, laboratory analysis could settle several of these open questions at once. If the recovered stones turn out to be ordinary chondrites, that's by far the most common outcome in the meteorite catalog, and the story ends as a well-documented but otherwise unremarkable fall. If instead they turn out to be achondrites, specifically from the howardite-eucrit diogenite family associated with the asteroid Vesta, that would place this object in the same rare category as 2 other recoveries from earlier this year, landing just 9 days apart back in March. A probable diogenite from a daylight fireball over Europe, and a confirmed urilite from the Ohio event. 3 meteorite recoveries inside a 10-day window against a worldwide average of around 10 a year was the single hardest physical fact to explain away from that spring's cluster of activity. And it has never been fully accounted for. Measuring the cosmic ray exposure age of any recovered stone would also reveal how long that particular fragment has been drifting on its own, independent of whatever larger body it originally broke away from, which is about as close as anyone can currently get to a real answer to where all of this actually came from. So here's what's worth keeping an eye on. Watch for any recovery announcement out of Douglas County over the coming weeks, and if one comes, watch closely for what classification follows. Watch for whether anyone publishes a proper radiant analysis covering the second half of this year, one that actually tests direction rather than just raw counts, since that's the real open question, and it's answerable with data that already exists. And keep an eye on the Cascade infrasound record, because those 5 volcano monitoring stations just proved, almost by accident, that instruments built to listen for one kind of hazard are quietly picking up on a completely different one. This particular rock got caught only because instruments aimed at volcanoes happened to be listening in the right place at the right time, and even with all of that data in hand, nobody can say with confidence where it actually came from. That's not a scandal. It's simply the current state of our ability to watch the sky, and it's exactly why the next one will arrive without warning too.